Now let's go a little bit further. Put the cheese on the cracker, if you will. Okay. Let's talk more about carbon. Why not? Carbon is the name. He's the reason for the season at this point, right? He's the name of the game when it comes to organic chemistry. Now, we know carbon is in group 4A, along with silicones, germanium, et cetera, right? And so when we learn in Chem 101 is that the same group means that you have the same chemical behaviors. So yes, silicone and not just these group 4, but other things can catenate and bond to themselves, but it's not going to be stable enough to bond to itself for that long of a time. And so again, we want things to be stable. Carbon is small enough to make good, strong bonds between other carbons and other elements, not just, of course, hydrogen, but of course, heteroatoms like oxygen, nitrogen, etc. Right? Also, let's go back to what we talked about when we were talking about atomic properties of carbon. We know that carbon is in period 2. Everything below that has those low energy d orbitals that are available to be attacked or occupied at any moment. So that makes them more reactive, right? And then if we go even further back to our introductory video, we know that silicone, yes, it can be unstably catenated to another silicone, but to make things more stable, we know that silicone is going to attach to our oxygen and make those silicone, oxygen, silicone bridges, which make up all of our geological world, right? Rocks, sand, soil, etc. So silicone is going to do that. Whereas carbon, again, it's all about the ability for carbon to bond to itself and other elements. Okay? So a carbon-carbon bond, we can get into more details about that because now it's like, yeah, if we're going to go back to 101, we might as well go ahead and do that, right? So a carbon-carbon bond has a certain amount of energy. And this is going to be the energy it's going to be taking to build or break bonds. Why is it important to learn about building and breaking bonds and the amount of energy? Because that's where reactions are, okay? So when we're thinking of organic compounds, we're waiting for areas where it's like we want to know what bonds are stable, what bonds are not stable, what bonds can become reactive, what bonds cannot, okay? So a carbon-carbon bond is actually more strong or has more energy than a silicon-silicon bond. And that's again due to atomic size and of course bond strength that we see here. And then the bond energy of like carbon-carbon, carbon-oxygen, or even carbon-fluorine, they're very similar to one another. And so when you have bonds that you're making, that means that carbon can make not only stable bonds, but when it's making bonds with other elements, it also continues to stay stable. They're all in the same relative bond energy, which is very important because we don't want things to all be different, causing more reactivity, okay? So again, something that means that they're very similar means that their enthalpies are very similar as well, or again, how much heat is needed to break or make new bonds in these reactions. So carbon compounds can undergo a variety of reactions and remain stable, which is going to help us understand its diversity, right? That's the whole goal here. So not only can we say, okay, carbon is able to make all these single, double, and triple bonds, we also can now say it can make these single, double, and triple bonds with the carbons and all these other things and remain stable. So it's kind of like very perfect. It's almost like the Goldilocks of organic chemistry, right? Not too hot, not too cold, just right there in the middle, right there in perfect. All right. Also, carbon does not break the octet rule. We're bringing that back, and it only uses those s and p orbitals. So it makes it easier for us to kind of memorize things when it comes to hybridization as well. Okay? So I would just always say carbon. It's reactive enough to change, but it's stable enough to exist for a long time. And then finally, what I want to also talk about, because we'll get to this later when it comes to carbon, is that it's actually very modular. And so what that means is it's made up of pieces. So I can take a piece of an organic compound, attach it to another organic compound, attach it to another organic compound. Let's give an example. Let's talk about nucleotides, for example. And nucleotides make up our nucleic acid like DNA and RNA. And so they're organic compounds, and when they attach together, they help create the single strand RNA or double helix of our DNA, for example. Okay? All right, so we can see that we did go into a bit much detail about carbon's ability to make stable bonds, which contribute to, again, its ability to catenate and therefore make millions of different compounds. So we got to get into the diversity of it now. Now we're moving away from just carbon as a single thing, an entity, and we want to think about carbon attaching to other carbons and the diversity that can come around from it. And let's do a little throwback as well from the other videos. We're talking about bonding. We're talking about bond energy. We're talking about size. We're also talking about the ability for those bonds to rotate if they're single or double. Of course, double has more restriction. We're talking about so many layers just to learn about carbon because it's just so important to organic chemistry. Another reason why Carbon Man exists, okay? Showing all those potential bonds. showing them at the different orientations, and of course, orientation in 3D map, and also showing that carbon hydrogen bond to make sure we're reiterating this is an organic compound. All right, folks.